Hey everyone, my name is Mark, and I looked at the Google Quest Q&A. So just a little bit of a background around me. I've been attending this meetup as well pretty recently, and it's been quite an interesting experience to see different types of data science projects, and specifically the sister group, which has been reviewing code papers, has been pretty useful as well. I mean, just last week, we looked at Hopfield networks, which gave me some intuition into self-attention models in work, which we'll be seeing here today. So I got my master's in IT at UNSW, and I'm primarily interested in natural language processing, computer vision, and recommender networks. I'm currently looking for data science and data analyst positions. And if you're interested, please feel free to connect with me on LinkedIn. Just another note, if you have any of the questions during the presentation, just let Matt or Steven or Bruce know, and they can interrupt me or interrupt me as we're going through the presentation. So generally, the overview we're going to be seeing here today is that we have a general challenge description, then a basic exploratory data analysis. The evaluation metric they used here was Spearman's correlation coefficient. There wasn't much of a leaderboard shakeup, but you'll see some interesting things here in terms of the top 5 competitors, and then my basic conclusion. So basically, this challenge was about humans versus machines. So machines require a specific domain area or a hyper-focused question in order to give a particular answer, while humans require more context or require a little bit more detail with regards to having a more multidimensional answer. So the metrics are quite different in terms of the way that humans and machines compute. So Google decided to utilize their crowdsourced labs, which is dedicated towards NLP, to sample Q&A questions from 70 different Stack Exchange sites in what they say is a common sense fashion. I don't know what that means, but they didn't elaborate any further. And they said the same thing with regards to the way that they provided classes. The way that crowdsource works is that it's similar to Mechanical Turk. They give users a prompt and a particular example, and then they rate it according to whatever metric that they're trying to collect. So in this case, that's what they did for 30 classes in this particular data set. So the aim here is to create intelligent Q&A systems that can reliably predict context the same way that humans do, without having to utilize some complicated set of guidelines. So the competition ran between November 22nd of 2019 to February 10th of 2020. They were 5 top spots, with the first spot being offered $10,000 and the last spot being given about $1,000. There were only 3 requirements that they mentioned in the competition guidelines, which is that the CPU notebooks would run in less than 9 hours, the GPU notebooks ran less than 2, and that all training should be done offline, or testing should be done offline. The interesting thing is that they mentioned they did have a separate thread for external data, which included disclosures about using Hugging Face, which is the PyTorch library for many of these NLP models, a TensorFlow hub for similar implementations in TensorFlow, as well as a 50 gigabyte dump of Stack Exchange data, which I'm not certain everyone utilized, but I mean, it's a tempting resource since there was only around 6,079 rows in the training data set, and clearly that was insufficient for some of these teams. But we'll see more as we go into these competitors. They were given three files. So the training data set contained 6,079 examples, along with of 40 columns, 10 of which were features and 30 of them were classes. In the testing file, they were given 476 examples with 10 of them being the features, and the submission CSV contained their respective predicted or true values for those classes. So, sorry.
Couple questions. Oh, actually, if we're going to see the data, that's great. I'll hold off on that question. But for if you can go back one slide.
Sure.
The 9-hour compute time, this is just for running inference, right? This is not training. You're essentially uploading a model, and then there's a limited time for it to run predictions on the data. Is that right?
Right. That's correct. That's correct. Yeah, it was a notebook-only competition.
That seems like quite a long runtime for an NLP inference task. Is that accurate? Or I haven't done much in the NLP, so.
Yeah, but I guess, 2 hours is pretty low. It might just be the lowest that they can realistically do on Kaggle. I don't think it makes sense to have like a 10-minute inference time or anything.
Right. And specifically, actually, the second team that won this competition was actually struggling with this issue, but it may have been more to do with the model they selected, which
I guess
we'll look into further. Yeah.
It prevents you from having like hundreds and hundreds of models in your ensemble, I guess.
Right.
Can each parameter, if it's NLP, can each parameter have like pages and pages of data? So it's actually quite a large data set, despite it not having that many values, like some dimension. Are they phrases or sentences or paragraphs or?
So you're saying for specifically whether the particular columns can have a very large length of text, and yes, it's possible for them to have that, but that wouldn't be sufficient in terms of training, since you wouldn't have enough examples of that for that given, different examples for that particular set of classes. So you need to have a variety within your data set in order to learn that distribution. Does that make sense?
Yeah.
Okay. So specifically going into the data set, what classifies as a unique example is that the question title and question body and the answer. So what that means specifically is that for a given question and their respective body, there could be multiple answers. So a unique body ID was assigned only to a particular title, a question, the respective body, and then a unique answer. In addition to that, you have within those 10 features, you include the question username, the answer username, their respective profile URLs, the URL of the question, and category and host. The 30 classes were split into two, or you could be seen as split into 21 classes for the questions that assessed whether the body was critical, whether the question was conversational, whether it had multi-intent, whether it had type spelling, type instruction, and so on. And the answers had 9 classes as well, with different abstractions like helpful, information, instruction type, and so on. So in terms of visualization, I decided to showcase a slice of the 10 features. So what you're looking here is the question title, question body, answer, and category and host. So I removed both the username and username, URL, and so on, the remaining columns, since for the purposes of visualization and for further data exploration, it doesn't seem useful to look at those particular features since we want to learn more about the sentiment or with relation to those classes. And with regards to the question set, it's a similar set of slices. So a slice through those 21 classes. By the way, for all of those classes, they were bound between 0 and 1. So you never got a value above 1, and you never got a value below 0. And the same goes for the answer set. So when I was trying to do further visualization, I decided to break it down by finding the number of unique questions per category. So you do see that the total number of sites here is that for culture is 12, and the number of unique questions for that is 539. For life arts, it's 9. For science, it's 12. Stack Overflow, there's only 1 site. And for technology, they had 31. If you add up all of these, you only get 63 sites. And in the total, you get 330 or 3,771 total unique questions in the data set. A second thing to consider here is that 2 of these sites, that's the mechanics and the electronic stack exchange, was labeled with 2 different categories, which might impact the way that competitors could, if they utilize category embeddings, it may have made an influence in their ability to predict. So that's specific to the training set. And then to the testing set, something similar is also seen here, but in total, you only see 56 sites. And similarly, but you do see all 476 unique questions, so which indicate that there is a one-to-one relationship between the question title, body, and answer. So there's only 1 answer for every question in the testing data set. And this similar issue is here where the electronics stack exchange was labeled both technology and Stack Overflow or technology and science. But combining the 2 together, you only see a total of actually 64 sites. So it's possible that the remaining 6 sites must be available only in the private data set. Any questions? So to see further distribution for all of the other classes, for the question classes, you can see that for some of the questions, there seems to be more are left skew in the data set, showcasing more examples with only a singular value. Others are more uniformly distributed. Which is going to play a much larger role in the way that they are scored in the final evaluation metric. So specifically, to keep an eye on is the question spelling column, where unlike on all the other metrics, there's, I believe, only 10 examples with less than with a value greater than 0. But you can't see it here because of the resolution. And with regards to the answer set, you can see that there's much more of a variable distribution between the different answer sets or answer classes. And so there's more of a better chance of predicting the answers compared to the questions. So looking further into for a particular body or for a particular set of examples for a category, life arts and culture follow the general English syntax and structure, so nothing special is there. But the science category questions and answers included special latex expressions. which were pre-printed and appended with the $ symbol. And technology and Stack Overflow contain code snippets and logs, and so variables in camel case and in snake case, so on. So in my approach, I decided to use a pre-processing pipeline using Spacy. So utilizing the $, I removed all the LaTeX expressions. Then I replaced all the escape characters with space. I replaced all the punctuation with space, and then to generate my tokens for the three columns: question title, question body, and answer, I generated a set of tokens by splitting on the space as a delimiter. Then I did further post-processing to check to see that there were no tokens that contained digits or special characters. That was not a stop word or didn't have a length more than 3 or less than 3. It's simply because some of these were acronyms. So to eliminate some of them, I just picked an arbitrary value of 3, and that seemed to have helped. Then to lemmatize those tokens, I had to initialize a second Spacy pipeline. In my implementation, it appears that by creating a custom tokenizer, it drops the part of speech tags, part of speech pipeline that is a part of the default implementation of Spacy. So there's no way to create a lemmatizer pipeline, initialize a lemmatized pipeline separately to that of the original Spacy. So I had to create a second Spacy pipeline to get a proper lemmatized terms. So to better visualize what's going on here at the, once I got all the tokens, I then wanted to understand more about what terms were either unique to a category or were more frequently used. So when I tried to look at more terms that were more unique to a category, there were around 10,000 or 16,000 terms for either the question title, body, or answer. So it was very difficult to figure out what those specific terms were that were particularly unique. And specifically, they had a count of at least 1 or 2. So to better visualize it, I looked at the words that were more frequently used. So that's greater than the 75th percentile. So what you're looking here is the most common words in culture in both the title, body, and answer. So you can see there are similar tokens like word that exists across title, body, and answer. No exists in body and answer, and so on. Also, you can see that there seems to be domain-specific words here as well. So English is here in culture, as well as question, usually, so on. And you can see this trend across the different categories. So here's the most frequent words in the title, body, and answer, and the same things you can see here as well with domain-specific tokens here available as well. So lens, water, different question, students, images. And it's more apparent here in science, where you can see probability, number, answer, voltage, energy. And the same trend across from Stack Overflow, but here you see more words than compared to the other categories being used more frequently, but this might be more of a function of just the long code snippets or function variables that are just called. So there's more information, or there's a longer body to deal with. So that's the reason why you see more words with higher frequency here. So it's not a combination of just the general English plus alone, it's the English plus the codes and logs. So you do see something specific like string, HTML, function, code, And the same thing here with technology as well. So to go into the evaluation metric, they particularly use Spearman's coefficient. So basically what that means is that for your predicted values versus the true values, you're trying to make sure that both of them are monotonically related. And that means that if one of them is increasing, then the other one should. And if the other one starts decreasing, the other one should as well. But you can see that can create some issues in terms of the certain classes that you want to predict. And that means specifically in instances where, like with question spelling, where there's such a massive skew towards zero, if there were more examples or more predictions that were non-zero, it could greatly influence your score. So that had to be considered. Also, in order to deal with the discrepancies between different distributions of classes, many teams utilized a form of thresholding to help boost their scores.
I have a question about this. Is the Spearman's coefficient calculated per feature, per predicted feature, and then the coefficients for the different features are combined somehow?
The way I understand it is it's done for all features together.
Okay. The Spearman's coefficient is kind of new to me, so it wasn't clear to me how to do it in that sort of multi-dimensional way. Maybe that makes sense.
Right. Yeah.
Okay.
So specifically for the leaderboard performance, so the top 5 teams here were Baby Morph, Birds and Holy Grails, Sakami, Babaconda, and Jigsaw, and CGI. So the 2 top ones here, or most interesting thing here of note is Birds and Holy Grail contains the Kaggle Masters from NVIDIA. And specifically, they did their entire project in 2 weeks, and they were able to only lose they were in the public leaderboard on the 3rd spot, and then they only got bumped by 1. And the team Biblimorph benefited from some posts made by Christoph Henkel. So they were able to boost their score because they were able to utilize BART. But we'll look into that a little bit later. So specifically, Biblimorph utilized a combination of four models. They used the BERT base, both uncased and cased. So for those who don't know, uncased is basically all tokens that are lower cased, and cased that considers all tokens of varying cases, because certain tokens may have different, in uppercase may have a particular meaning in the model. So that's why they're trained separately. And then they use the Roberta base, and finally BART large. And BART large is the model that Christoph Henkel had referred to, and was what Biblimorph used at the end. So the general architecture here is that they fed in the question title, the classification token, followed by a separation token, the question body, separation token, followed by the answer and the separation token. And then they fed it into either BERT or Roberta and BART. Then they took all of instead of taking the final layer from the hidden state and softmaxing, they took the classification tokens from all hidden states, and then softmaxed it and sent it into the linear layer while using multi-sample dropout. But they utilized 3 additional tricks before they fed it into the model. So the first thing that they did was language modeling. And this is where that massive Stack Exchange dump comes into play. They took a subsample of that, and they took 7 million of those questions, and then they used the mass language modeling task of the BERT pipeline to train on specific tokens in the data set, and then sentence order prediction from the Albert pipeline to determine something similar for those for all those specific classes. Features. In addition, they also predicted 5 additional classes, which was question score, question view count, question favorite count, and answer score. And then they used that to refine their model. And as we saw earlier, there were a lot of unique tokens specific to a particular domain. So they extended the case vocabulary for LaTeX symbols and code snippets and so on. The second technique that they utilized was pseudo labeling. So pseudo labeling is basically a technique where for this additional Stack Exchange data, they basically trained an existing training data set with their labels and trained a model to determine the labels for that data set. And then for the new data set, for the 7 million data set, they created new labels for that data set. But one of the problems that they were encountering was that when they utilized group k-fold cross-validation, but when they initially took the pseudo labels from each of those folds, it ended up resulting in overfitting. And predominantly it was because there are similar tokens that you can see in both the technology and in Stack Overflow. So essentially what it was doing was it was returning labels from the original training CSV, which they considered as leakage. And that's why when they were doing their validation, it was basically giving them a higher validation, but that was resulting in overfitting. So instead, what they decided to do was they for that specific training set in that fold, they labeled the data set at that particular level, which produced less accurate labels, but reduced the number of examples with train leads.
Hey, Mark, can we stop here for a second? I just feel like I need to think through this out loud for a little bit, because I think there's a lot of good concepts here, and I'm not sure I fully understand them. So the training set and the testing set that were given in the competition, there was very few samples of questions and answers there. There was only like 6,000 or something, right?
Yeah.
And so what some teams took advantage of, because that's not enough data to train your own language model or to really do much with. Like, you can essentially just take a pre-trained model and hope for the best, maybe fine tune it a little bit. So what they did is they found this big dump on Stack Overflow that contains like hundreds of thousands of samples of questions and answers. And then given all of this extra data, they said, okay, now we have enough for, oh, actually this is an additional 7 million. Okay, so they have, what is SE questions?
Stack Exchange.
Stack Exchange, okay. Stack Exchange questions, and now they're going to train a language model. Do you know if they trained it from scratch or if they fine-tuned their language model that they already had?
They trained it from scratch. Yeah.
Okay, so they train a language model from scratch. That's what mass language model means, is essentially in BERT. There's 2 ways to train a language model. You can train it, one, by like randomly masking out or hiding words and then having the model predict that and then try to learn these missing words. And then the other way is like to try to predict the next sentence or to try to tell if two sentences follow each other. But I guess in this one some of the questions were really short, so you didn't have multiple sentences. So unless that's what SOP means. Is that what SOP means?
Sentence order prediction, yeah.
Oh, okay, so they are doing both of those. Okay, great. But the problem is on all this data that you don't have those features that are in the competition. So you don't have, how useful is the question or how useful is the answer, all those features you described earlier. So what they wanted to do is they wanted to be able to come up with some way of using this data in their actual classification training steps. And so what they would do is they would start by just training a model on the 6,000 on just like the training set that was given by Kaggle. So they train a model there, and then they use that, and then they try to get that model really good, and then they use that model on all these hundreds of thousands of samples, and they label it essentially. And then in the next round of training, they'll use this much larger data set for training the classification tasks. Okay, but then they found that when they did that, when they found that when they used their best model, which is essentially probably a stacked ensemble from the 6,000 questions, they were overfitting to the labels in the 100,000. So instead, what they did is they would train one model on one fold from the 6,000, and then use that. Oh yeah, this is where I'm a bit confused. Okay, so they came up with some hacky way to try to get around that and to try to add some more diversity to the labels that are in the 100,000 samples, essentially, by not getting the best possible model that they could from the 6,000, but by training lesser models that didn't get to see all the data and it was not a stacked ensemble or something. And so, yeah, creating a lot of diversity in these 100,000 samples. I'll probably have to read up a little bit more on that later, but I think I kind of get it at a high level. Did all that sound right?
Yeah, that's correct. Yeah.
Okay, great. Sorry. Hopefully, that was helpful for me to think through. Hopefully,
No, it's good. It's good.
That was helpful for me to listen to as well.
Okay, awesome. Okay, I'll think out loud.
Okay. So one more trick that they utilized was post-processing. So as I mentioned earlier, thresholding was causing issues with their Spearman's correlation. But in their implementation, they decided not to threshold based off of random parameters. They decided to bucket predictions according to the distribution of the parameter of the classes in the data in the training set. And the two other, as I mentioned earlier, the two other things that they utilized was multi-sample dropout. So multi-sample dropout is generally dropout removes neurons in the from the previous layer, and then allows the model to generalize. But in multi-sample dropout, what that allows you to do is across different samples, you can drop out different neurons, and that effectively simulates duplicating the batch or the number of samples being trained on within the model, and that will give the model a better chance to generalize. And then they used group K-fold specific to the question title groups. So the models that they provided, they did not give any, while they did say that they used differential training rate, learning rate for both the encoder and the heads, in their code, they only offered one learning rate for each of the models. So in the BERT's case, they had a maximum sequence length of 500 tokens, 26 tokens for the title, 260 tokens for the question, and 210 for answers. And they used a batch size of 8, learning rate of 2e to the of -5. For Roberta, similar parameters for sequence length, title, question, and answer length, but they varied batch size, and the learning rate was 1e -5. And BART, the same thing for sequence, title, and question and answer length, but they kept the same parameters as BERT with batch size of 4 and learning rate of 2e to the 5. And then the final step that they used was blending. And they gave more importance to BART and to BERT, and equal weight to both the BERT pre-train and a Roberta pre-train with the pseudo labels.
For that blending process, is there any way that those values were quantified, like what they gave those weights, or is it just kind of trial and error, fine tuning?
They didn't go into any details, but they said I would believe they used it empirically. Yeah, they determined that. As I was mentioning earlier, the BART model was not something that they actually had considered. So in the second competitor, Christoph Henkel, had put a post up on the thread 1 week before the competition deadline, and they were the main reason why he didn't implement it was because there was no implementation in Hugging Face. So when these guys saw that post, they decided to, I guess, implement it on their own, and that took them about 3 days to train on a 1080 Ti, and that this model alone gave them the best score compared to the rest of their models. So that's probably the main reason why they gave such a larger weight to BART compared to the rest. So the second competitor here was BERT's in the Holy Grail. And again, as I mentioned earlier, this was an incredible feat by these guys, where they basically utilized, within 2 weeks, they came up with all these models and basically maintained their position on the leaderboard. So they utilized a total of 5 models. They used a dual transformer Roberta base, dual transformer Roberta large, dual transformer XL net base, and the Siamese transformer Roberta base with a softmax layer, final softmax layer. There was a slight discrepancy in the way they described it. In the beginning, they mentioned they used Roberta base, and then towards the end, when they were summarizing, they mentioned they may have used Roberta large. But their problem with using Roberta large was that they were saying that they couldn't fit it into memory, and they had to. The only way they were able to do that was by selecting for a batch size of 1. And by training on a V100, and by training with a batch size of 1 and setting it to a floating point 16 setting. So I don't believe they were able to use Roberta large. So it looks like they may have used Roberta base instead. So their main architecture was dual transformer, and Siamese transformer for the last one. So for the dual transformer, basically what that means is they had a separate transformer for the question and a separate transformer for the answer. The input into the question transformer was both the question title and question body. And for the answer transformer was the question title and the respective answer. And then both transformers are sent into an average pooling layer, and concatenated, and then sent into a fully connected layer, and then used to predict the final target. In the Siamese transformer, similar to the dual transformer, question title and question body were sent in, and then question title and the answer. But this time it got sent into a single transformer, which then was average pooled, and the weighted average was then sent into a fully connected layer. While it shows that there are 30 classes being predicted here, they actually decided to switch the classes to an ordinal representation. That means it was an ordered view. So for a given class, they created at least n unique new classes, and in total they created 170 classes. They utilized a differential learning rate for the transformer of 3e to the 5, and for the model it was 0.05. They utilized a cosine scheduler for training 3 epochs, and 1 epoch they used for warm-up. And for optimization, they either used the Adam W or Adam with a weight decay of 0.01 and an effective batch size of 8. And they used the binary cross entropy for their loss function. Their final runtime was 2 hours with some wrangling, as mentioned earlier, to fit 5 models within the competition requirements. So they also had 3 key tips when they were training their model. So they used binary encoded targets. So that basically means for a given class, for a set of unique values, they encoded the class as t greater than a particular unique value. And then the way that they predicted the value for each original class was that they took the predictions for that particular unique value from the fully connected layer, and then they subtracted them from each subsequent set of values to get the original value. And then because in this example that we're seeing here, everything is equally spaced, you can then compute the mean of the target value as p of 0, p of 1 over 3, and p of 2 of 3. And you don't use the last value. So that's how they got the final target value. So for their validation scheme, they also used a 5-fold group K fold, but this time they used it on the question body. However, they were having the similar problems as the previous team, where they were getting poor cross-validation, and this time it was because they believe there were similar questions between the training and testing set. So they believe that since there was there was only a single question and answer pair that was there in the testing set, while there weren't that many in the training set. So what they decided to do was in each fold, they randomly sampled 100 single question and answer pairs. And then they took the median of those 100 samples. And then they decided to ignore the predictions from the question spelling, since it was causing further errors in their score. And they got a final cross-validation by the mean of all those 5 folds. And in their write-up, though, they mentioned instead of 100, they were utilizing 1,000. And then they took a median of those 1,000. I'm not exactly certain where they got 1,000, if they're using 5-fold group K fold, but no one made a mention of it in the discussion. So I chose to just keep the 100 in here. Yep, go ahead.
Yeah, I'll say that the group K fold is really important here because you do have duplicate questions in your training set that have values tied to that question, right? So if you're randomly splitting without the group K fold, you're going to get those same questions in your training set and in your test set that are going to be evaluated on those features that you predict for, and you're not going to have any way of knowing if it's actually learning some generalized knowledge or not. I think we've had this come up a few times in the past meetups, and in fact, Kiri did a whole presentation on how important training and testing splitting is. And so, like, I definitely see that as being like a really important concept here. Group K-fold is important. And then just given that they have 6,000 questions in their training set, it seems to make sense to sample 1,000 as opposed to just 100 of those for training. So I think they probably just mistyped that, or they were doing just a test for the 100 case. But yeah, I feel like they meant 1,000.
Okay. Yeah. So yeah, then it must be 1,000 single question answer comparison. And then they did the similar thing for post-processing. They did threshold clipping. They didn't elaborate how they got selected optimal thresholds, but that's how they clipped using some form of optimal thresholding. But it didn't work for their question spelling column. And so what they decided to do was to hard set the first 6 or the highest 6 predictions and to 1, and then they set the rest to 0. So a little bit more detail about the dual transformer. They took 512 question tokens and answer tokens, and they sent that in. And then they took the output of the last layer, averaged over those 512 tokens, and concatenate them together. And then they fed them into 30 individual fully connected, fed them into 30 little 2 fully connected layers, so that each head would then gain some individuality. And then for the Siamese transformer, they took the output from every layer, which was 512 tokens. And then they averaged it over the 512 by 756 tensors. That resulted in a single 758 representation. And then they took a weighted sum followed by a single prediction head. The third competitor here used an even greater number of models, used more variety here. He used LSTM with universal sentence encoding. Then he used BERT base cased, then followed by BERT based uncased, 2 of those. He used BERT large, both cased and uncased, and two of each. The Albert base, Roberta base, GPT2 base, and XLNet base. So then he did some text truncation. So he did some pre-truncation and post-truncation. He didn't elaborate as to what he specifically truncated, but that was one of the things he used. So as Matt was mentioning earlier, he decided to fine tune it by generating head and tail tokens for the BERT models, for BERT-based models. And then he discovered in his experimentation that by stacking 2 linear layers without activation, improved the performance for some of those models. So in some of our implementations, you're going to see that. Then for his training strategy, he did min-max target scaling. So he found the minimum and maximum values, and then for in the predicted columns, or sorry, for the feature class for the classes, the true values, and then he subtracted the min, and then he divided it by max minus the min. Then for those which had minor positive or negative samples, then he created large weights for them, and then he used what he called a Gaussian error linear unit activation on top of BERT. Then he also used a similar cosine warm-up scheduler. And then he used this function called EMA, which I believe is exponential moving average. He didn't elaborate on that either, but it appears to be a function that he used to improve his cross validation score. And as I mentioned earlier, he said that some models were also using category embeddings. So that may have improved his performance as well. For post-processing, he decided to use golden ratio search to determine the thresholds, and then did prediction clipping based off of those thresholds. And finally, he used blended it by using tree parsing estimator optimization, which is a Bayesian optimization technique by using the Bayes rule on tree learning to finally blend it. So so this goes to the question that Keith had earlier. Here he used a particular optimization technique. So specifically about golden ratio search, it appears that this is the main purpose here is to find the minimum value for a given function. So the way that works is you specify 3 points, and within those 3 points, you determine which of those points is the lowest, and then that's how you know that particular interval includes the value, and then you iteratively search for a new value and update the interval according to which interval contains the minimum value. But the difference that this has over this traditional search is that the golden ratio stands for the original two values. So between, in this case, like A and B. So that should result in at each step that you're iteratively searching for, it should always be proportional to the golden ratio. And this will prevent your minimum from getting close to either the min or the max value, getting close to either the F0 or the max value of your function. I think I explained that as much as I could. But if anybody else understands this better, please go ahead and explain it. Okay, well, I'll move ahead then. This was a model he utilized for his LSTM. So he put his concatenated question plus word embeddings into a bidirectional LSTM, and then he max pooled and average pooled it before sending it into a linear layer. Then he sent his answers through an embedding layer and then into the bidirectional LSTM, and did the same thing, max pooling and average pooling. Then for the concatenated questions, he then sent it into a universal sentence encoder, and the same thing for the answers. And all of the outputs get sent into a linear layer and then finally through a recurrent linear unit for activation, and then through a final linear layer for the 30 classes. For the BERT model, he sent everything together. So the question title followed by separation token, question body, and answer into a traditional BERT model. Then the sentence output is sent in with the first token, the question average, the average of the sentence output, answer average, and then the last token. And then here's where he found out that by sending it into a linear layer first and then into a second linear layer, he got an improved performance. And in his second implementation of BERT, he, instead of going through a sentence output, he just took the first token from all hidden states and then sent it into the linear layer. For Albert, similar to Bert, he used the question title, question body, and answer, and he sent it into a sentence output layer. Then he averaged it and took the first token and sent that into a linear layer, then sent that into an activation layer for a TAN-H. And then the last token gets sent into, and all three get sent into the linear layer. For Roberta, something similar. They sent the question title concatenated to the body and then followed by a separation token and an answer. And then he sent that into a Roberta model, the sequence outputter. Then he took the first and last token and sent that into the linear layer and then followed by another linear layer. And then used XLNet with the similar inputs, but this time he used the classification token out of the sentence output layer and then sent that into a linear layer. For GPT-2, similarly to previous models, he sent in question title, body, and answer, but this time he took the separated token of the answer head from the sentence outputter and the last token, and then he average pooled the sentence output and sent all three into a linear layer and into a final linear layer. He didn't explain as to why combining the two resulted in better performance without activation. So I can't really elaborate as to why it did better. And then the final fourth and fifth competitors here were Babaconda and CGI. So Babaconda utilized two, in total, 6 models, so 3 BERT and 3 XLNet. And then for each model, they placed the input, the question title and body, and then they predicted 21 question classes, and then they inputted the title and answers, and then predicted on the 9 answer classes. And then they only used the body and answers to predict all 30 classes. And then they finally used a linear layer across all 3 and concatenated the output. And this same architecture applies for the 3 XLNets that they used. For post-processing, they utilized a technique where for the final fully connected layer, they determined the maximum number of voters, or they iterated over the range of voters to determine the largest number of voters that returned the best prediction. And then those for the final number of voters from all of those classes was then applied to all those classes specifically to get the best result. And then they returned the mean between the true and predicted classes. For CGI, they said they originally experimented with the Roberta model. However, what they pointed to was resource entirely in Mandarin, so I can't say for certain. However, they seem to have finally settled on Roberta base, Roberta large, and XLNet base. They also used host and category as part of their features. And other statistical features like answer token length versus question token length. They also look for specific domain, specific words and symbols, so they removed those ones. And with post-processing, they said 0 and 1 resetting. I'm going to assume that means thresholding, and they didn't mention anything further other than that. And then they mentioned stacking with those 3 models, with the Roberta and XLNet base getting 0.3 and the Roberta large having the largest weight, which was 0.4. And then I just included the shortcut that the Babaconda and Jigsaw winners provided, because they believe that this is what helped them get their 4th place. So as you can see, they iterated over. So originally they believed that 90 total voters for each column, And then basically for each predicted value, they calculated the score that they would be getting for each voter. And then they calculated the correlation between that particular voter and the true value. And finally, they determined the best max voter. And then they applied that to all of their columns and finally returned the mean between the true and the best voter predicted value. So in conclusion, the simplest models with the most intuitive design won this Kaggle competition. Certainly, if the second team had trained that BART model and included it with theirs, it would have worked even better. Catering to a specific topic domain can also better train the model, so I can notice the different distributions between different types of data. Certainly, there are different approaches in post-processing, which also improve performance. So that's a definite consideration to keep in mind. And then, as we've seen earlier, using large data sets is in fact key to refining these models. And clearly also utilizing transfer learning from all these existing models help these individuals get better results. So that's my presentation.
Awesome. Thank you, Mark. We have a few minutes for questions if anybody has any questions.
So maybe kind of a meta question, but being relatively new to a lot of this, like this is very specific models and NLP would you have any suggestions as to where to kind of get a start on like familiarizing oneself with this, like with NLP and maybe just some of these packages and the like how like they're how they're actually working?
Well, if you're specifically looking into NLP, then I'd say like first to get a better understanding of the domain area, if that's makes sense. So specifically, like figure out how like refer to Medium posts like towards machine learning. That's a great resource to look into. And then towards machine learning mastery is another site where they cover similar across a much wider range of topics. And specifically, the bigger challenge is like recognizing what is like feature selection. So generally in tabular data, you can combine different features together and you can get a better understanding of what's going on. But in NLP, you need to know like there is that issue of too many words. So that's where shortening words through lemmatization, through stemming. So lemmatization is basically like getting it to the root word. Like stemming is basically trying to look for the longest common suffix. So that's not as useful because that's not going to be a word that you can look for. And then converting those set of tokens into a way that the machine can learn. So embeddings is another key area to keep in mind here. So ones that you should look out first is word2vec and glove. So word2vec is more of a local understanding of relationships between words, while glove is more of a global representation of those same sets. And then Facebook has released fast text. So that's also a useful embedding, word embedding tool for even learning on words that don't exist in the dictionary. So even fast text can do that even better. Yeah. And then for these models that we discussed, they're all on Hugging Face. Yeah.
Yeah, Hugging Face is really a great library that's come out in like the past year or two that makes a lot of this a lot easier. So in terms of like implementing it, it's actually quite easy. You could follow guides and you could reproduce a lot of these models that these people won with, essentially just following blog posts and following guides on Hugging Face. Another great word is, I like that you pointed out Medium. There's just a lot of really great blog posts about NLP that you can just kind of like Google and read through, and they explain it all really well. And I resort to those on a regular basis as well myself, because the field's just changing so much. But there's a course at Stanford 224, that's all the lectures are online or on YouTube. This is like one of the best courses for NLP as well. It'll take you all the way from like the very beginning about what people used to do, kind of introducing you to the deep learning stuff, and then kind of going through the fundamentals behind it all. It's probably a lot of information to learn, and you don't need it all to be able to introduce this stuff. But if you are interested in kind of how the math works, that's a good resource.
Yeah, that's part of it. And it's just like there is a lot of resources, but it's almost overwhelming sometimes. So I just thought maybe we could get a direction in that to actually more understand like the theoretical frameworks behind this.
Mm-hmm.
Like implementing is one thing, but understanding what you're doing is, I mean, I like that part. So
Yep.
No, thanks for all the resources, guys.
Yeah, no worries.
Okay, guess we'll call it there. So before we stop the recording, let's all give Mark a big round of applause. If we can all unmute ourselves. I think everybody is muted right now. And I'll count us down. 4, 3, 2, 1. That was really great, Mark.
Thank you.